Hi folks, so today we're going to work on drawing polypeptides. Remember that formation of a polypeptide results from dehydration of two amino acids in the ribosome. And in this question we're being asked to draw the structure of the pentapeptide, which is a 5 amino acid peptide. At the N terminus starts with R, L, E, Y, Q and ends at the C terminus. We have to draw it in the correct charge state at pH 11. So we have five amino acids in our peptide. Each amino acid backbone is made up of an N, an alpha carbon, and a carbonyl carbon. So our backbone will at least have this unit from every amino acid, and it'll have an N at one end and a carbonyl at the other end. Now when we make our polypeptides, what we're making is new amides. And so we want to string 5 amino acids together like this. Okay. One thing you can notice is that the carbonyls and the alpha carbons alternate every time. And so when you get on here, you want to make sure that that happens. Okay, so I have just drawn 5 of those units. I have my first amino acid, second, third, fourth, fifth, and you can count the alpha carbons or the carbonyls to get 5. And remember at the end we have OH, or an O at least, and on the other end we have H protons. Those are the N terminus and C terminus respectively, and those correlate to the N and C in the notation up here. So I have my backbone in there for now. I like to avoid putting on hydrogens on the nitrogens until the end because there's some amino acids that, or at least one amino acid that will disrupt that. We don't want to put them on too early. At pH 11, do you remember your pKa's? The N, our pKa is around 9. And for the C, it's around 2. So at pH 11, we are above both of those two pKa's. If our pH is above our pKa, we're deprotonated. Okay, so our N can be either positive or neutral. When it is protonated, it is neutral. So we have H2N there, not a plus. And our C terminus, the pK is 2, or deprotonated, and we are going to be negative at that point. It can be neutral or negative, and the deprotonated state is negative. So now we have a -1 charge overall. Now I'm going to start putting on my side chain. So my first one is R, which stands for arginine. Arginine has 3 carbons in its backbone. And then it has this thing called a guanidino group. In its deprotonated form, it looks like this. But here, our pKa is 12.48. Our pH is now below the pKa. 11 is below 12.48. And so we are protonated. So that means we have to add another hydrogen, NH2, and we have to add a positive charge on this side. So that's a protonated arginine. The next one we have is lysine. Lysine starts with this alpha carbon and forms a little L at the end, which is my easy way to remember it. Lysine is, or leucine rather, not lysine. Lysine is L. Lysine is K. Leucine has a little isobutyl group at the end, so that's one way to remember it as a little L at the end instead of isoleucine, for example, does not have that. That's L. No titratable groups on that side chain. E is glutamic acid. 1, 2, 3. There are 2 CH2s in the side chain and then a carboxyl group at the end. pKa for that is, for glutamic acid, is about 4.07. Our pH is above our pKa, so it's deprotonated. Okay. Next we have tyrosine. On the next alpha carbon we have CH2, and we have a benzene, and an OH. pKa on tyrosine is 10.46. Are we going to be protonated or deprotonated here? pH is above our pKa, so we're going to be deprotonated in this case. So I'm going to go ahead and erase that out, that H. Okay. and we'll make this negative. Because our pH is above our pKa, we need to be negative. So our tyrosine is now deprotonated. And last we have Q. Q is glutamine, or Q-tamine as I like to remember it. And that has NH2. So essentially it's the same thing as this glutamic acid, but instead it is a primary amide, or primary amide. And a thing a lot of people will frequently mistake on this will be to try to add protons or take them away from this guy. There is no pKa for the side chain on glutamine. That's because, if you recall, this lone pair is actually delocalized into the amide resonance, and so therefore it can't be used as a base. And we don't ever encounter physiological pHs that are strong enough to pull off one of these hydrogens. And so don't try to deprotonate or charge our glutamine residue. Okay? So we don't have to worry about it. I'm going to erase all that stuff. But remember, any of the amines like glutamine or asparagine, those don't change in protonation states. Only the ones with titratable groups, the 7 titratable groups, and the N and C terminus will change. So one thing I like to do is just make sure that I haven't made any mistakes here. We are deprotonated at the N. We are protonated at the arginine. We are deprotonated everywhere else. So we can sum this up as a ball and stick model. We have 2 backbone groups. Our C terminus is negative. We have 1, 2, 3 titratable side chains. That one is for the R. And then we have L is not, E is, and Y is, and Q is not. So I drew this as a 5-group ball and stick model, and let's just apply our charges. We have a positive at the R, negative at the E, and a negative at the Y. And so overall, at pH 11, what is our charge? We are negative 2. Plus 1, minus 1, minus 2, minus 3. All that together is minus 2. Okay. So what are the charge forms that we could actually observe here? So we have, again, our 5 titratable groups. Okay, this is our N, R, E, Y, C. N is positive neutral. Arginine is positive neutral because it has an amino, has nitrogens in it. Glutamic acid is negative because it's a carboxy group. Tyrosine is neutral negative because it is a phenol, and C terminus is neutral negative because it is a carboxyl group. Our pKa's are around 9 for this, but actually the arginine pKa, if you were to look this up, it would be an actual value. I don't require you to know that, but you could look this up. I believe it's 8.99. Let me look. It is 8.99. Okay, so I'm going to go ahead and just edit that. On an exam, you wouldn't be expected to know these exact numbers, but I'll write them down specifically. Now, this is arginine N-terminus because arginine, if you look up at our structure, the side chain is directly attached to that group. You see that? So this is arginine's N, just like this would be glutamine's C terminus, which we will use in a second. Okay, so that's 8.99. Now, arginine, side chain is 12.48. 4.07 for glutamate, glutamic acid, 10.46 for tyrosine, and tyrosine's C terminus has a pKa of 2.20. So our charge states we could observe would be all the top states, all the protonated states, plus 1, plus 2, all the way to minus 3. Going through 0, our charge states would be these ones. And so we would observe 6 states, 6 expected, macroscopic, so we would have a 6 expected, we would have 2 to the 1, 2, 3, 4, 5 theoretical states, even though they may not actually be observable. So 2 to the 5th, 2, 4, 8, 16, 32. that right? 2 to the 5th is 32. Yep. But only 6 expected. What do those actually look like? Well, let's draw them out. So we're going to, our +2 is going to be the protonated for all of them. That's going to be plus. Plus. And then we have 3. At the pKa of 2.2, we're going to substitute the +1 form. +1 form is going to switch here at the C terminus, so it's going to become negative there. But our other one's still positive. So that's the +1. At a pKa of 4.07, these are sequential in order. We would switch to the 0 form. At that pH, we would put our glutamic acid to negative, negative, positive, positive. Our next pKa we would switch that would be, next in line would be 8.99. And that would be where our N terminus would switch. It would still be negative, negative, positive, but at this point we've now gone neutral. Next we would have 10.46, where our tyrosine would switch. That is this one, negative, 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 positive. And finally, at 12.48, our last group, our arginine would switch. Okay, so that would be negative, negative, negative. +2, +1, 0, -1, -2, and -3. That's all 6 of our observable titratable forms. So we'd see these in these ranges. We would, for example, see the +2 below 2.2. We would see the +1 between 2.2 and 4.07. You can see that here. 0 form we would see between 4.07 and 8.99. So that physiological pH. -1 we would see between 8.99 and 10.46 in that limited little window. And -2 we would see between 10.46 and 12.48. And finally, the -3 we would see above 12.48, which we wouldn't see very frequently at all. So those are the forms we would expect to see. We could calculate the fraction of any of those if we wished, just setting up the appropriate math. Let's do that real quick. Let's figure out how much of the -1 you would expect to see at a pH of 9. So, -1 form, what's that look like again? Let's scroll back up. -1 form is this guy. -1, -2, -1. That's our -1 form. And recall our pKa is 8.99, 12.48, 4.07, 10.46, and 2.20. Okay. So if I wanted to figure this out, how much of this is, what is the concentration of our negative, or fraction of our -1? What we would do would be to set up the fraction deprotonated at the N, fraction protonated at the R, deprotonated at the E, protonated at the tyrosine, and deprotonated at the C terminus. We have a fraction deprotonated at the N times the fraction protonated at the R times the fraction deprotonated at the E times the fraction protonated at the Y times the fraction deprotonated at the C terminus. And we would expand those. Recall that our equations for fraction protonated are concentration of H plus over Ka plus H plus for each of the groups. and our fraction deprotonated could be 1 minus that, or it could be Ka over Ka plus H plus. So use those correctly. We would apply our deprotonated ones to these 3, and we would apply our protonated fraction equation to these 2. Multiply them all together, we get our fraction, and we're done.